Sorry about that. All right, so when we were last talking, we were talking about these multi-dimensional potential energy surfaces, and we were taking an overhead view of them, where along this axis we have leaving group leaving, and along, sorry, I'll just blow that up a little bit. There we go. And on this axis, we have nucleophile attacking. We talked about how the pathway from here to here along the y-axis represents leaving group leaves to give you carbocationic intermediate, and then nucleophile would attack, whereas this diagonal pathway would indicate nucleophile comes in at about the same rate that the leaving group leaves. And then we started to change the structure of the alkyl halide, or the electrophile, and we watched how the concerted SN2 pathway and its transition state change. And one of the things that we observed, and this is based on calculations and observations, are that if we increase substitution on the carbon that has the leaving group, we're going to lower the energy, increase the stability of the carbocationic intermediate. So over here we have a methyl carbocation, which is very unstable. Here we have a primary carbocation, which is less unstable. And that does two things. It makes the SN1 pathway more feasible, though in this case the SN2 pathway is still lower in energy. But what this does is it pulls the potential energy landscape a little bit more towards this corner, such that the transition state shifts to involve a little bit less nucleophile attacking and a little bit more leaving group leaving. And we see this is true not only for the primary alkyl halide electrophile, but also if we have a secondary leaving group, there the secondary carbocation is more stable, so this corner of our potential energy surface goes down in energy, and that has the effect of pulling the transition state towards that corner. And if you look at what that does in terms of reaction coordinate, this transition state goes to more leaving group leaves than it used to be, right? We're moving from here to here. This is where we were before for the methyl leaving group. Now we're at the secondary leaving group. We have more leaving group leaves, and we have less nucleophilic attack. And that makes sense from what you know intuitively about substitution reactions, right? As steric hindrance increases, it gets tougher for the nucleophile to attack, so it makes sense that the leaving group would have to leave a little bit more. And of course, once you get to the tertiary alkyl halide, you can write what the transition state for that SN2 pathway would be, but it turns out that the SN1 pathway is even more favorable there. So this illustrates an interesting principle when you think about potential energy surfaces, okay? And that is, if you have this diagonal pathway that represents a concerted reaction, if you stabilize the corner, notice that this pathway connects two corners of our potential energy surface. If you stabilize the off-diagonal corner, the corner that's not along the concerted reaction coordinate, what this does is it pulls the transition state towards that corner in sort of a perpendicular direction. You can think of this effect as though the transition state were sitting on a surface like a sheet, and you pull down the corner. You lower one corner, the marble's going to roll towards the corner you lower. Okay, the analogy breaks down because, of course, if you lower the corner a lot, the marble will just roll to that corner. But remember that as we're envisioning this potential energy surface, this corner is really high in energy. But as we lower it, the transition state sort of gets pulled towards that corner, and that effect, if you lower the energy of this corner, then the transition state moves toward that corner perpendicular to the concerted pathway. Okay, so we might expect, if we could somehow make this proposed intermediate where the nucleophile attacks first and then the leaving group leaves, if we somehow made that structure more stable, the transition state would be pulled in that direction. Okay, that's called an anti-Hammond effect, for reasons that we'll talk about in just a second. But if for this continuum between SN1 and SN2, if you stabilize the carbocationic intermediate, the transition state gets more carbocation-like and less nucleophilic attack. Now, let's talk about what happens if we change things along the corners that are connected to the reaction mechanism. And the easiest way to think about that is to think in terms of nucleophilic reactivity. So what if we use a better nucleophile versus a poorer nucleophile, right? What do you expect for an SN2 reaction? If I, say, use a weak nucleophile like methanol versus a strong nucleophile like methoxide, the strong nucleophile will react faster or slower? Faster in the SN2 reaction, right? And so if we were to consider along this orange pathway and just take a slice of the potential energy surface and just look at the energy diagram along this pathway, here's the SN2 reaction, and let's say this is the SN2 reaction with a weaker nucleophile, and then here's the transition state and here's the product. If I use a stronger nucleophile, what that means is that my starting materials have been destabilized, they're higher in energy, and what this actually does, based on the Hammond postulate, is it moves as the starting material increases in energy, the transition state becomes more starting material-like. This is just another way of restating the Hammond postulate, right? Along the reaction coordinate diagram, two adjacent states that are close in energy are close in structure. So in terms of what this does to the transition state, if we raise the energy of this corner, if we destabilize this corner, what that's going to do is it's going to move the transition state more towards the starting material. And that is called the Hammond effect. All right, so changes at the starting material or the product will result in the Hammond in effects that are consistent with the Hammond postulate, changes off the diagonal with a carbocationic intermediate or with this anionic associated complex. That will cause the transition state to move not along the reaction coordinate here, but perpendicular to it. So what we have predicted for the SN2 reaction is that as you go to larger, more substituted alkyl halides, the transition state is going to become less nucleophile leaving and more leaving group leaves. And we've said, in contrast, that if you use a stronger nucleophile, the transition state's actually going to move further this way. Less leaving group leaving, right? And so that tends to agree intuitively with what we have learned about these substitution reactions. So this diagram sort of summarizes, let me just try to summarize again what we've been talking about. Sorry. And sometimes we can do multiple things at once. So if we have a reaction coordinate pathway, let's not even worry about what the reaction is. We have starting material here and product here. And let's suppose we raise both corners, all right? So we're going to raise the energy of this corner, and we'll also raise the energy of this corner. What's that going to do to our transition state? Well, raising the energy of the starting material is going to have a Hammond effect where the transition state moves earlier. Raising this corner is going to have the marble rolling on a sheet effect where the transition state's going to want to move perpendicular to the reaction coordinate. And actually, the overall movement of the transition state is just like vector sum addition, moves this way and this way, so the overall effect is to move the transition state here. And because these effects can cancel each other out, right? This effect moves you earlier here and earlier there. This effect moves you earlier this direction, but later this direction. And so overall, the change is here. Go ahead.
I don't understand why raising like the view corner.
Yeah.
I don't understand why it shifts the transition state perpendicular. That's why I was hoping it would shift it towards itself.
Right. Only along the diagonal does raising the corner shift the transition state towards the thing that's destabilized.
Okay, but up there, when you are explaining the SN2 reaction, where the living group, where the nucleophile attacks,
yeah,
the living group lives, I thought when if we make that transition state more stable, if we make that intermediate more like that living group attacking and more like the nucleophile attacking and the living group leaving, I thought the transition state would move towards that end rather than this other end.
Right. Well, so the example here is not quite the same as what I was doing below, because when I was talking about increasing the strength of the nucleophile, we were only talking about destabilizing this corner. It's hard to imagine for the SN2 reaction, substitution reactions, what this looks like. This involves a short bond between nucleophile and carbon and another short bond between carbon and leaving group. And that's unstable enough that I don't really have a good example for you about how you would make this more stable. So what we did for the substitution reaction is instead we considered, okay, how do I, what if I made a change here? And we talked about if I lower the energy here by making the carbocation more stable, the transition state moves to become more carbocation-like. It moves towards that corner. So similarly here, we're just saying, instead of saying we're lowering this corner, we're saying we're raising this corner. So if you lower the off-diagonal corner, you will move towards that corner perpendicular to the orange line. If you raise an off-diagonal corner, you will move the transition state away from the corner that you raised, again, perpendicular to that line. So this is another example. Suppose that you have an effect where you lower the energy of the top corner, which is connected to the diagonal. If you lower that energy, that's going to move the transition state further along to become more product-like. That is the Hammond effect. And then if we, at the same time, lower the energy of that corner, whatever this intermediate is, that's going to pull the transition state in this direction towards that corner. So the overall effect on our transition state will be that we move in the direction indicated by that arrow. Okay, so I'm sort of sensing a therefore what question here, like, okay, fine, but who cares? So I want to show you a couple examples where you can use this to reason through what's going on. The first is going to be some SN2 transition states that I calculated in Gaussian. And so what we're going to be doing is basically looking at these situations, and we're going to be looking at the transition state that I calculated, and we're basically going to be measuring what's the distance between carbon and the leaving group as a way of figuring out how far along this axis we are, and what's the distance between nucleophile and carbon to figure out how far along this axis we are. Okay, so I got to stop. All right, to give you a sense for how substitution at the carbon that bears the leaving group impacts the position of the transition state, I've calculated some transition states and energies using Gaussian for the reaction of cyanide with bromomethane versus bromoethane versus 2-bromopropane. Here is the transition state for cyanide reacting with bromomethane, and we can measure the distance between bromine and carbon at 2.2 angstroms. We can do the same for bromoethane, and that distance is 2.4 angstroms, versus 2-bromopropane, where that distance is 2.5 angstroms. So you can see that as we go from methane to ethane to propane, where the leaving groups on a methyl primary or secondary carbon respectively, in the transition state we are shifting to longer and longer carbon-bromine distances, indicating that the transition state is moving on the potential energy surface down the y-axis more towards leaving group having left. We can do the same with carbon distances, nucleophile carbon distances. In bromomethane transition state, the distance between carbon where the leaving group was versus the carbon at the nucleophile is 2.4 angstroms. For bromoethane, it's 2.4 angstroms, and for bromopropane reacting with cyanide, it's about 2.4 angstroms. So for this particular example, the carbon nucleophile distance doesn't change very much as a function of alkyl halide substitution. I've summarized these data in an Excel spreadsheet, where I've also shown you data for bond lengths in the isolated compounds. So in regular bromomethane, the equilibrium carbon-bromine distance is 2.02 angstroms. In the transition state, that bond has gotten longer out to 2.3 angstroms. Similarly, in cyanomethane, the distance between carbon and carbon is 1.5 angstroms, whereas in the transition state it's 2.4 angstroms. So you can see that relative to and these bond distances, carbon-bromine bond distances, do lengthen as a function of carbon substitution, probably because of sterics. Similarly, the carbon cyanide bond lengths increase as a function of substitution. But you can the key thing to see is what I illustrated in the figures is that as you go from bromomethane to bromoethane to bromopropane, the carbon leaving group distance is longer in the transition state. And this is an example of what we saw in those two-dimensional projections of potential energy surfaces. All right, so I've written down the numbers based on what we observed, okay, and that can give you a sense for how far along the leaving group leaving versus nucleophile we're at. For the methyl halide, the leaving group carbon distance was 2.3 angstroms, and the carbon nucleophile distance was 2.4 angstroms. Notice we predict, as we stabilize this corner, that the transition state's going to move to more leaving group having left, and perhaps less nucleophile having come in. We don't necessarily see, for the calculations I've done, we don't necessarily see a change in where the nucleophile is for methyl versus primary, but we see a fairly substantial change in how much leaving group is left, from 2.3 angstroms to 2.4. Okay? And then as we go to the secondary alkyl halide, again, where the nucleophile is hasn't changed a lot, but where the leaving group is has changed quite a bit. All right? So this is an example of the kinds of predictions you can make using this type of diagram. Let me show you an example of some actual chemistry, an actual reaction where this kind of analysis helped the researchers understand the nature of a catalytic reaction. So here is a reaction that is it's the hydrolysis of a phosphoester. Okay, and you're having water act as a nucleophile, attacking phosphorus, and a leaving group leaves. The reaction mechanism is SN2-ish, meaning we have a nucleophile attacking, we have a leaving group leaving, but we're going to have two different reaction coordinates. One is the distance between the phosphorus and this oxygen. So that's the nucleophilic attack. And then the other is going to be the distance between this oxygen and this phosphorus, or in other words, leaving group leaving. And for the uncatalyzed reaction, and we'll talk later about how you actually make these measurements, but they calculated that the leaving group was about 37% gone. And there was substantial new bond formation between oxygen and phosphorus. Okay, so then they used a bridge dicobalt catalyst to make the reaction go faster. And this is the proposed catalytic reaction sequence. You have this bridging hydroxyl group in your catalyst, which loses a proton, making this oxygen more nucleophilic. At the same time, our phosphoester is actually coordinated to each of the cobalts. Then the nucleophilic oxygen from the catalyst attacks the phosphorus, and the leaving group leaves. That gives you this catalyst-bound sort of phosphate group. And then in a, let's see, Second step, hydroxide has to come in and attack the phosphorus, and then that oxygen gets reprotonated, and then this group would not bind anymore. Okay, and presumably these subsequent steps are fast. So let's consider the two-dimensional potential energy surface looking down, and on one axis we're going to see phosphorus oxygen bond formation or nucleophilic attack, and on the other axis we're going to see leaving group leaving. Okay, so here's our diagram, and here's the reaction coordinate pathway. On this axis we have nucleophile attacks phosphorus, and on this axis we have leaving group leaves. Okay, and this is the catalytic shown here are extremes along the reaction pathway. So at this corner we have starting material bound to the catalyst. Here we have nucleophile attacks without leaving group leaving. So this is an intermediate that would be proposed if you have a pentavalent phosphorus. And actually that's not that unreasonable. I think there are some cases where you do see pentavalent phosphoruses. Okay, at this corner you have the other extreme, leaving group leaves first and without any attack of the nucleophile. And then here is the product where the nucleophile has attacked and the leaving group has left. One of the things they noticed in terms of the transition state for the catalyzed versus the uncatalyzed reaction, remember I told you for the uncatalyzed reaction, the leaving group was 37% gone, but there was still substantial nucleophile phosphorus bond formation. So that represents this dot. This is the uncatalyzed transition state. And there, leaving group is 37% gone, and nucleophile is quite a bit bound. In contrast, for the catalyzed reaction, they observed that the leaving group is 77% gone, and the oxygen phosphorus bond formation is almost 100% complete. How do they explain that? Well, they argued that the catalyst creates strain. Notice that in the starting material you have a 1, 2, 3, 4, 5, 6 membered ring. In this corner, this intermediate, and this corner, you have a bicyclic system, a 6-membered ring bound across the middle to make 2 4-membered rings. So they reasoned that that strain should take both of these corners and raise them in energy. Okay, and then what effect should that have on the transition state? Well, here's the corner that lies along the reaction coordinate. If we raise this corner in energy, what would that be predicted to do? Well, that should move the transition state along the reaction coordinate. Should move the transition state along the reaction coordinate in this direction. And that's just, again, an example of the Hammond postulate, right? If you go from starting material to product and then you destabilize the intermediate, the transition state is going to look a lot more like the intermediate. And so in terms of reaction coordinate, you've moved closer to that intermediate. At the same time, they destabilized this nucleophile attacks without leaving group leaving corner. That's not along the reaction coordinate. So raising this corner has the marble on sheet effect of pushing the transition state perpendicular to the reaction coordinate along this direction. And you sum both of those together and the transition state moves here. Okay? And so this gives you a sense for not only how to use these diagrams to predict changes in reaction mechanism and transition states, but it also shows you in one case how a catalyst actually works. You know, we say, well, a catalyst changes the mechanism of a reaction, or sometimes we say a catalyst stabilizes the transition state of a reaction. In this case, the catalyst actually destabilized a couple of intermediates, and that moved the reaction further towards completion. Yeah.
So why does it stay on the red line? I'm kind of missing that detail. I understand the shifting.
Why does it have to stay along the red line? I don't know.
I get the fact that it goes that way. I just don't know why it went to the dot on the red line.
Yeah. I guess you're getting an incomplete picture because this is only capturing, this is showing you the lowest energy pathway through this potential energy landscape. In reality, what we would have done is we took both edges and raised them up in energy. And so perhaps the way this example is illustrated isn't that great. You might have expected it to show you a new pathway that would look something like that. I don't know. So I don't have a good explanation for that. In fact, I think that probably the orange line is imaginary in the sense that what they were able to measure was just what this point is and what that point is. Yeah. Okay. So that sort of leads to the question, well, how do I know what this pathway is? Well, in a lot of ways, as long as you know starting material, transition state, and product energies, and geometries, you already know everything you need to know. But you can do calculations that start at the transition state and start to make changes in either direction, and you can trace out the lowest energy pathway in terms of geometry, from starting material to transition state and from transition state to product. All right. Anything else? Okay. So you may encounter that, and we'll return to this here and there as we discuss reaction kinetics, but that's sort of the end of chapter 7. Now what we're going to do next, did I press record? Yeah. What we're going to do next is in chapter 8, focus on experimental techniques for probing reaction mechanism. And this is cool because we're going to get at some of these issues as to how do we know a reaction mechanism is a certain way. I think I mentioned last time that you may have had people, I don't know why I can't write and talk at the same time, reaction kinetics. You may have had people ask you about a particular reaction mechanism before, and why do we have to deprotonate first? Or I happened to be walking in the hallway and I heard a couple of students talking about OChem, and one of them was saying, well, once I get to this intermediate after a Grignard reagent attacks an ester, how do I know that the leaving group can leave? And a related question is, how do you know that that's the reaction mechanism and that the leaving group leaves? So we're going to talk about some of these things. One of the biggest tools for studying reaction mechanism, one of the most commonly used among organic chemists, is the kinetic isotope effect. All right. And when I first taught this class, I only vaguely remembered learning about kinetic isotope effects, and I thought I sort of understood them, and then the stuff here presented here actually made it quite a bit more complicated than I thought it was. So, what do you know about kinetic isotope effects? What have you heard? It's usually related to taking, most commonly, it's related to taking a hydrogen and replacing it with a deuterium. The reason you do that, and you can do C12, C13 kinetic isotope effects, but the relative change is bigger for hydrogen versus deuterium, right? You're doubling mass for hydrogen versus deuterium, whereas for carbon 12 versus carbon 13, you're only changing it by like 1/13, whatever that is. Okay, so it's related to measuring reaction rates with hydrogen versus deuterium at a certain carbon. Okay. So you're going to substitute one isotope for another at an atom where bonds are breaking, or at an atom where we're rehybridizing during a reaction. Or you might put the isotope substitution not at that atom, but near an atom, okay? So there are two places where we might make hydrogen versus deuterium substitutions. We might choose, as I said, at an atom where bonds break in a reaction, or at an atom that rehybridizes, that changes geometry, changes hybridization in a reaction. And then second, we might put the hydrogen versus deuterium nearby the atom identified in one. And generally, the kinetic isotope effect is given as a ratio of rate constants. So you'll measure a rate constant for a reaction with hydrogen, either at position 1 or position 2, and then you'll measure that same rate constant with deuterium at either position 1 or position 2, and then you will divide the rate constants, and it's generally given, just it doesn't have to be this way, but this is generally how we say hydrogen rate constant over deuterium rate constant. Okay? And what does this number tell you? Well, if it makes no difference at all whether you've got hydrogen or deuterium at a given position, then the atom or bond where you made the substitution is not changing in the rate determining step of a reaction. So, as an example, suppose you think that a proton has to be removed either during or prior to the rate determining step of a reaction. Then you do this experiment with that proton and you see no effect at all. You just learned that that proton is not involved in the rate determining step of the reaction. Now we'll talk about why being involved in the rate determining step of a reaction should make you have a kinetic isotope effect. But if you don't observe one, that's pretty good evidence that that particular proton's not involved, and that carbon is not involved in the rate determining step of the reaction. It's a debate as to how close to 1 it needs to be totally ignored. Kinetic isotope effects can be small, but still significant. If the reaction is faster with hydrogen versus with deuterium, that is, if this ratio is greater than 1, that's called a normal isotope effect. And if the ratio is less than 1, that's called an inverse isotope effect. As to what the implications are, we're going to need to talk about a little bit of PChem and vibrational bond vibrations to get a sense for that. But just globally, this is what people will say. If you hear people talk about a normal isotope effect, they mean it's faster for hydrogen than for deuterium. If they say inverse, they mean it's slower for hydrogen than deuterium. So in addition to the words normal and inverse, you're going to hear a couple other words about kinetic isotope effects. You're going to hear people talk about a primary kinetic isotope effect, KIE, and this comes from breaking a bond between whatever atom and hydrogen or whatever atom and deuterium in the transition state of the rate determining step. Second, you'll hear people talk about secondary kinetic isotope effects. And this comes from not breaking of a bond involving that hydrogen or deuterium, but this involves rehybridization of an atom to which to which hydrogen versus deuterium is attached. Transition state of rate determining step involves rehybridization of the atom to which hydrogen or deuterium is attached. That's one interpretation. Or it could mean a secondary isotope effect could simply mean that whatever bond you've replaced is far from location where bonds are changing. In the rate determining step, RDS, of the transition state. Okay, so this gets a little bit tricky. What I remember learning as an undergraduate about kinetic isotope effects were that if you consider this an energy diagram for a bond between some atom X and hydrogen, and on this axis we have energy, and on this axis we have bond distance between the bond between that whatever atom X and hydrogen versus deuterium. There's at sort of infinite distance, the energy is 0. As they get closer, the bond starts to form. There's some minimum in energy, and then as we go too close, we start to get repulsion that overwhelms the bond, overwhelms the attraction between the electrons and the nuclei. And breaking of a bond would involve going from here all the way here, right? Bond breaking. This sort of energy level represents complete bond homolysis or homolytic bond breaking. Now, it turns out that no bond ever just adopts this lowest energy. Bonds have what are called 0 point energy. Even at 0 Kelvin, there's some residual 0 point energy and some residual bond vibration. And so the kinetic isotope effect comes from the fact that the carbon-hydrogen 0 point energy, which is related to the vibrational frequency of of the carbon-hydrogen bond is higher, that 0 point energy is higher than the carbon-deuterium 0 point energy. So it, in theory, requires less energy, easier to break the carbon-hydrogen bond than it is to break the carbon-deuterium bond, because this energy difference in blue is less than this energy difference in purple. Now, we're imagining a reaction in which this will make the biggest difference if the reaction involves breaking of the bond between X and hydrogen versus deuterium. And we're imagining that these blue and purple lines respectively represent the activation energy for the reaction, right? That is, in order to break the bond, you've got to go from here to here. That makes the assumption that the transition state basically involves complete bond homolysis, bond breakage. That's not always the case. We've seen, looking at those transition states that I just showed you, that bond breakage is often not complete in the transition state. So to the extent that we don't have to get all the way up here, the difference in activation energy between hydrogen and deuterium might actually not be as big as we've shown here. But this is the sort of origin of what we're going to be talking about. Now, that's at a very sort of 30,000 foot level. We're going to get into the weeds a little bit and try to get a sense for where this comes from. It's going to involve a little bit of PChem that I don't understand that well. So we'll try to go through it in a way that's understandable to everybody and that's most useful. So we'll do that next time.